Welcome. Today, we are going to follow one single command on its absolutely incredible, high-speed journey through the mind of a computer. We're going to see exactly what happens inside that little chip that powers, well, everything we do. So let's just start with the biggest question of all, right? We all know computers are smart, but what does that even mean? How does a machine really process information? How does it go from your mouse click to a program opening in literally a fraction of a second? Well, the answer to that question lies right here in this amazing component, the Central Processing Unit, or CPU. It's the command center, it's the engine, it's really and truly the brains of the whole operation. It processes every single instruction that makes a computer do its thing. So here's the roadmap for our little instruction's big journey. We'll start with the CPU's main job, then we'll follow an instruction as it gets fetched and decoded, watch it get executed, and finally, we'll look at what makes this whole process happen so mind-bogglingly fast. Okay, let's dive right into the computer's brain. We're going to start with a big picture of what the CPU is actually designed to do, from running your web browser to calculating all the crazy physics in a video game. You see, everything a computer does, no matter how complicated it looks on the screen, is actually broken down into millions of tiny, simple instructions. And the CPU processes every single one of them using this core, endlessly repeating cycle. It's basically the heartbeat of all modern computing. And that three-step process is called the fetch, decode, execute cycle. Seriously, this is the fundamental rhythm of computing. Fetch the command, decode the command, execute the command, and then repeat, billions of times a second. So let's break that down. Okay, so let's follow one single instruction as it gets called up for its mission. This all kicks off with the fetch stage, where the CPU has to go and retrieve its next command from the computer's memory. First things first, the CPU needs to know where to look. That job belongs to a special little piece of memory inside the CPU, called a register, specifically the program counter. You can think of it like a bookmark. It's always keeping track of the exact location in RAM where the very next instruction is waiting. So the address from that program counter gets sent over to another register, the Memory Address Register, or MAR. Think of the MAR as the CPU's personal postal worker. It takes that address and gets ready to find that specific mailbox out in the computer's main memory, which is RAM. And this address travels along a dedicated pathway called the address bus. It's like a one-way street just for memory locations. Now, once that address is found in RAM, the actual instruction, the data itself, is pulled out and starts its journey back to the CPU. But this time, it travels on a different highway called the data bus. This one's a two-way street, made for data to travel between the CPU and RAM. And it arrives at yet another register, the Memory Data Register, or MDR. And from the MDR, the instruction is sent to its final stop for this leg of the trip, the current instruction register. It is now safely inside a really important part of the CPU called the control unit, all ready for the next stage. The fetch is officially complete. So, just to recap, because this is super important, we have two separate pathways, right? The address bus carries the where, the memory location, and the data bus carries the what, the actual instruction. Keeping those two separate is absolutely key to the whole operation. It makes sure the address and the data don't get all jumbled up, so the CPU always fetches the right thing from the right place. All right, so what happens next? Our instruction is now sitting inside the control unit, but right now, it's just a string of ones and zeros. The CPU has no idea what to do with it yet. So now what? This is where the real magic of the decode stage happens. The control unit basically acts like a translator. It takes that binary code and looks it up in its built-in dictionary, which is called an instruction set. This dictionary has every single command the CPU knows how to do. Is it an add command? Is it a move data command? The instruction set tells the control unit exactly what action needs to be performed. The mission is clear. The instruction has been fetched from memory and it's been decoded. Now it is time for the CPU to actually carry it out in the execute stage. So the control unit now becomes the conductor of a tiny, high-speed orchestra. It sends out these precise electrical signals through a third pathway, the control bus, to coordinate all the other parts of the CPU, telling them exactly what to do and exactly when to do it. You can really think of that control bus as the conductor's baton, directing the whole performance. For instance, if the instruction is a math problem, like add these two numbers, the control unit signals the arithmetic logic unit, or ALU, to get to work.
The ALU is the part of the CPU that handles all the calculations and logical stuff. And if there's a temporary result from that calculation, it gets held in another special register called the accumulator.
And just like that, our instructions journey is complete. But you gotta remember, this whole cycle happens billions of times every single second. So what makes one CPU faster than another? Let's talk about performance. The speed of a CPU isn't just one thing. It's really determined by three main factors all working together: the number of cores it has, its clock speed, and the size of its cache memory. A core is basically a complete processing unit inside the CPU. So a single-core CPU can really only do one thing at a time, but a multi-core CPU can handle multiple instructions at the exact same time. This is what lets your computer truly multitask. It's the reason you can listen to music, browse the web, and have a download running all at once without it grinding to a halt. Next up is clock speed, and this is measured in gigahertz. This number tells you how many cycles the CPU can run per second. So a 2 gigahertz CPU can perform 2 times billion of those fetch-decode-execute cycles every single second. And what's really wild is that this incredible number, that's for just one core. If you have a quad-core processor, that's 4 cores, each running at this absolutely blistering pace. And finally, there's cache. See, that fetch stage takes time, because believe it or not, RAM is pretty far away from the CPU in computer terms. Cache is a small amount of super fast memory that's built right onto the CPU chip itself. It's like a little scratch pad, keeping the most frequently used instructions and data right next door so the CPU doesn't have to wait for them to arrive all the way from RAM. And this slide just sums it all up brilliantly. Think about it like this. More cores are like having more brains to work on a problem. Clock speed is how fast each of those brains can think. And cache is like each brain's short-term memory, the important stuff it keeps right at the front of its mind. All three of these are critical, and a bottleneck in any one of them can slow the whole system down. Which brings us to a final thought. We've seen how a computer thinks today, right? Following this fundamental cycle at just incredible speeds. But as this technology keeps getting faster and more powerful, what new kinds of thinking will our devices be capable of? The possibilities are just mind-boggling. Thanks for joining me on this journey through the CPU.